Yeah. Hi. So, today we are going to do something called as the normalization problem, which is a part of module 4 in our DBMS. So, this is a very important question in our DBMS, which easily will give us 10 marks. So, let's begin. So, in every question of normalization, they'll give you two things. First is the name of attributes, and second is functional dependencies. Okay, so these two they will give you in the question. So, for example, in this question, the attributes are A, B, C, and D, and the functional dependencies are AB is dependent on CD and C dependent on A. So, with the help of these, we should be able to figure out if the relation is in 1NF, 2NF, or 3NF. Okay, so that is our question. Let's begin. So, the step one while solving this, okay, is to check and figure out the candidate key. Okay, check and figure out the candidate key. So, how do we do that? So, how do we do that is there are basically two steps to do this. First step is to check for candidate key, we have to see what attributes are not present in the RHS of the functional dependencies. Okay, so let's see that first. So, what are the two functional dependencies? The two functional dependencies are ABCD and CA. So, in these two, what is not there in the RHS? Only B is not there. Correct? So, which means B is always present in the candidate key. Okay, now let's proceed further how to do it. So now uh, let's find the closures. So the procedure is called finding closures. Okay, so how do we do it? Let's take first AB is related to CD, C is related to A. Okay, now let's consider AB as our first candidate key. Why? Because when we are taking B alone, there is no functional dependency with B alone. Okay, like for example, B to C is not there. Okay, then B to D is not there, but AB is there. So because AB is there, we will use AB as a whole. So now AB, if you take, we have to make sure closure means finding out all the different ways that all the other elements can be derived from one particular element. Okay, so from AB, let's see what all can be derived. We can derive AB and we can derive CD because AB is directly related to CD. So with this, we can derive all the four elements of ABCD using AB. Now let's take, just for example's sake, let's take another candidate key. From this, we can only derive A, B, and C. Why? Because C is related to A, but B is not separately related to C and D. A, B is fully related to C and D. Okay, so that's why BC will only give you ABC. Okay, so so far this is the part where we find the closures. Okay, now what is the candidate key? The candidate key is AB. Okay, or in this we can have more than one candidate key. Why? Because if you take ABC as a candidate key, this also will give you all the four elements, and ABD will also give you all the four elements. So that's why our candidate keys are AB, ABC, and ABCD. Okay. Now from these three candidate keys, what is a super key? Super key means the minimal candidate key. So minimal candidate key means that's a super key, which is basically AB, because AB has the least number of elements, least number of attributes. Okay, that's why this is the super key. So far, this is the concept of finding closures. Now let's go to step 2, which is finding 2NF, checking 2NF. Okay, now in checking 2NF, there are two criteria which you have to satisfy. The first criteria is the RHS should be a non-prime attribute, and LHS should have, so RHS should be partially dependent, not be. Partial dependency should not be there. Okay, so these two conditions you check. Now from here, what are the prime attributes? Prime attributes means the attributes which are part of candidate key. So in this case, it's all of them, and the non-prime attributes are nothing. It's an empty set. Okay, so all of them are prime attributes. So now according to 2NF, the RHS should be a non-prime attribute, but in this case, in all of these, RHS is a prime attribute. So that's the reason here, as all functional dependencies have prime attributes in RHS, so it satisfies 2NF directly. Okay, this is a condition for 2NF. Next, 3NF. Now, what is the condition for 3NF? There are two conditions. Now, let's take alpha related to beta. Alpha should be a super key, or beta should be a prime attribute. Only these two conditions will work for 3NF. Okay, now let's check every single one of our relations. AB to CD. In this, LHS, is LHS the super key? Yes. So it verifies. Then we have C to A. Here, LHS is not a super key, but RHS is a prime attribute. So this also satisfies. Hence, 3NF is satisfied. Okay. So far, this is how you check 1NF, 2NF, and 3NF. Now let's see the last one, which is BCNF. So if 3NF is satisfied, you will go to a condition called as BCNF. So for BCNF, there's only one condition: LHS must be super key. LHS must be a super key. Okay. How does it work? AB is proportional to CD, C is proportional to A. Okay. So if LHS is a super key, must be, that means your AB is a super key, right? So that means this is satisfied. But in the second case, C is not a super key because super key is AB. That's what we saw in the beginning, right? Super key is AB. So because super keys are AB, C to A does not have a super key. Thus, BCNF is unsatisfied. Okay, which basically means the relation is in 3NF. This is the conclusion of this question. Okay, so any other queries you have related to this concept, please approach me personally. I will explain further. But so far, this is how you solve a normalization problem, which is the part of module 4 of our DBMS. Thank you.